When we consider in-building deployments, we consider a number of factors. One, how do we eliminate interference? How do we eliminate all of the user experience challenges that you'd have in a typical small cell deployment for buildings? So how we do that is by implementing a CRAN-based architecture. That architecture centralizes the baseband processing within a controller and then distributes the signal across multiple radios in the coverage area. What we're demonstrating here today is our ability to deliver 4 times cell capacity within a single cell environment. This allows us to deliver 300 megabits per second of capacity within a single cell system. When we consider users being distributed within a coverage area, we would normally have 50 resource blocks that we can allocate to those users. However, with smart reuse, we're able to quadruple that, delivering 200 resource blocks that we're able to schedule. You may ask, how are we able to achieve this, and especially within a single cell system? Well, we do that by tracking the user's location within the radio environment and finding opportunities to create virtual sectors for each of those users when we need to give them data. And you can see then that if we have 3 different users, in this case user A, user B, and user C, they each need to be served data. And we've detected from the reference signals that they're sufficiently separated from each other that we can give them these non-overlapping virtual sectors. That allows us to then serve each user different data, sharing the same resource block over the environment, as you can see here. So user C gets his data, B gets his data, and A gets his data, but we're doing this all on the same resource block. This, in effect, gives us 3x reuse for the first PRB. In our next example, we'll look at resource block 2. We have a different set of 3 users. They each have their own virtual sectorization within, and they again each get their own data, also now delivering 3 times reuse for the second resource block. In this last example, we'll then look at a set of 4 users. Those 4 users here are in different locations, and in this case you can see the network sectors, and they can be different sizes. This allows us to tune and shape the environment to best serve the needs of the user and to ensure that we're delivering the maximum quality of experience for all users inside of the one cell system. And in this case then we're delivering 4 times reuse on the 3rd resource block. And what's significant about this is that we're completely eliminating interference by pre-knowing how we need to schedule the users based upon where they are. When you look at traditional small cell systems, they are unable to do this in an effective way because all the decisions are being made independently by each of the small cells. And any attempt to react to that interference is done after the interference has already occurred. We're able to completely eliminate that interference, and through virtual sectorization, we're able to multiply the sector capacity, thus increasing the overall spectral efficiency and the quality of experience for users. Therefore, the net effect is that we're delivering multiple levels of reuse in the environment in a very dynamic way.